Hey everyone, and welcome to The Explainer. We're jumping right into a completely fascinating and, honestly, an increasingly urgent cryptographic problem today. We're looking at this. How do we mathematically prove whether an advanced, highly intelligent AI is internally contradicting itself? Because look, as these AI models get more powerful and start acting autonomously, they're making literally billions of probabilistic claims about the world. But what happens if those underlying claims fundamentally conflict with each other? Well, today, we are diving deep into a really groundbreaking 2026 paper by researchers from EPFL, Mila, UC Berkeley, and MIT. They've actually figured out exactly how to catch an AI in a logical lie, and it's brilliant.
So here is our roadmap for this detective journey. We'll start with the AI trust problem, define probabilistic consistency, tackle the verification challenge, compare explicit versus implicit claims, break down the interactive PCP protocol, and finally wrap up with what this means for safe scientist AI. Okay, let's get into it.
Section 1. The AI trust problem, or when supercomputers contradict themselves. So to set the stage here, modern AI models kind of act like they know everything, right? You can ask an advanced model a billion different conditional questions, and it's going to give you a super confident answer every single time. But as we start using these models as autonomous scientific reasoners, or even as safety guardrails, we absolutely have to have a way to make sure their underlying logic isn't fundamentally broken.
Okay, let's dive into this. I want you to picture yourself as a detective. You're sitting across an interrogation table, and on the other side is this highly intelligent, incredibly sophisticated, and potentially deceptive AI suspect. It's throwing all sorts of claims at you. Now, our job isn't necessarily to prove that the AI knows the ultimate, objective truth of the universe. No, our job is just to prove that its story mathematically holds together. But how in the world do you interrogate a suspect whose brain contains billions of parameters?
Well, the very first thing we need to do is draw a hard line between truth and consistency. A model might be factually wrong about the real world. That happens. That's a calibration issue. But what we're talking about today is consistency, meaning, can all of this model's probabilistic beliefs mathematically exist simultaneously in one single, coherent world? Consistency is the absolute prerequisite for trust. If a model is inconsistent, it's not just a little uncertain. Its reasoning is fundamentally structurally broken.
Moving to Section 2, what is probabilistic consistency? We're going to build a mathematical alibi. To catch our suspect, we really need to know the exact mathematical rules this AI has to follow to be considered trustworthy. So here is our formal definition. Probabilistic consistency is a state where a model's probabilistic claims correspond to a single, coherent joint distribution over all variables. You can think of this logical alibi just like a detective checking timelines. For example, if an AI claims that event A is 90% likely and that event B given A is also 90% likely, but then it turns around and claims event B overall is only 80% likely, well, mathematically, that's literally impossible. 90% of 90% is 81%. The story completely falls apart. There is no single probability distribution that can support all those claims at once.
Now, looking at this mathematically defined structure, it brilliantly illustrates how we actually used to handle this problem. Traditionally, we dealt with what's called a collection of probabilistic claims, or CPC. You would just have a straightforward, explicit list of claims. It starts with the probability of event y1 given x1 equals p1, and it goes all the way down the line to ym given xm equals pm. Back in the day, if a system gave us, say, 50 of these claims, our detective verifier could just manually check the math to see if a single distribution satisfied them all. It was super straightforward and completely transparent.
But that brings us to Section 3, the verification challenge and navigating the black box. Because we have hit a massive wall. The sheer scale of the modern AI problem makes that old manual checking process completely impossible now. We aren't dealing with 50 explicit claims anymore. We are dealing with models making billions of interconnected claims implicitly.
Just compare the old method to our new reality here. Previously, a verifier could sit down and just read a short, explicit mathematical proof from start to finish. Done. But modern models, they are massive, interconnected neural network black boxes. The claims aren't neatly listed out for us. They are implicitly baked right into the weights of the network itself. Because a neural network processes these highly complex, nuanced contexts, the possible claims it makes are exponentially large. You literally cannot just read it in full anymore.
And just to put the sheer scale of this into perspective, at the time this paper was written, systems like OpenAI were serving over 2 billion queries a day. 2 billion! A human verifier, or honestly even a traditional computer verifier running in polynomial time, cannot possibly check every single implicit probabilistic claim for consistency. If the witness you need to prove consistency is a joint distribution over all those variables, the resulting data is doubly exponential in size. We are talking about an inconceivably massive amount of information.
So, Section 4, explicit versus implicit consistency. We have to find the sparse witness. Because how does our detective actually win against an opponent who can bury the truth in an exponentially large haystack? We need a serious mathematical breakthrough here. We need a way to prove this consistency without checking every single data point.
And that's where this crucial discovery comes in, the Karathi-Ordery witness. The researchers used some really complex convex optimization to prove that if a model is consistent, you don't actually need an infinitely massive distribution to prove it. Instead, you can prove it using a very small, quote-unquote, sparse witness distribution. Specifically, they proved you only need a support size of m+1 points, where m is your number of claims. Plus, by introducing just a tiny tolerance for error, they proved this witness can be written out with logarithmic precision. So in our detective terms, they proved that to verify a massively complex alibi, you only have to check a remarkably small handful of highly specific, low-precision clues. It's a total game changer.
Section 5, the interactive PCP protocol, which is our interrogation technique. Now that we have our theoretical sparse witness, we still have a big problem. The untrusted AI is the one generating it. So this is the core cryptographic solution the researchers designed to actually catch an inconsistent AI in the act.
Because even our shiny new sparse witness is still way too big to just download and read in full, the untrusted AI prover encodes it into what we call an exponentially long proof oracle. Now, our verifier, our detective, doesn't try to read the whole thing. Instead, they engage in an interactive, probabilistically checkable proof, or ICPC. This means the verifier is spot-checking very specific, randomly selected locations inside this massive oracle, continuously looping and interacting with the untrusted AI to test its claims.
Now, what's really interesting about this slide is exactly how that spot checking works mathematically. We are looking at the squared inconsistency formula. On either side of the equation, we have the AI model's circuits evaluated at a random point. Right in the middle are these really complex expressions representing the marginal probabilities. This massive equation would normally take exponential time to compute, right? But it's reduced by the verifier. The verifier forces the AI to summarize this massive sum, and then uses a cryptographic protocol called sumcheck to verify that summary. They do this by checking just a single random data point against the proof oracle. It is incredibly elegant. To actually pull this interrogation off without getting tricked, our detective uses a specialized toolkit known as Reed-Muller cryptographic gadgets. First up is verank, which runs a quick global check to guarantee that the massive proof oracle actually represents a valid probability distribution in the first place. No negative probabilities, and everything sums perfectly to 1. Next up is vermarginal, which lets the detective interactively verify those middle marginal probability formulas we just talked about. And finally, sumcheck, which is honestly like magic. It's the tool that reduces verifying an exponentially massive sum all the way down to verifying a single randomized point.
To make all this theory work on an actual, functioning neural network, the researchers conceptually break the model down into two distinct halves. You have the probability circuit, or circuit P, which makes the actual prediction. And then you have the confidence circuit, circuit Q, which outputs exactly how confident the model is in that specific prediction. By mathematically separating the prediction from the confidence, the verifier can appropriately weight any inconsistencies they find. So, if the model contradicts itself on something it had zero confidence in anyway, the penalty is super low. But if it confidently contradicts itself, the formula flags it immediately as a major lie.
And this brings us to the absolute, undisputed brilliance of this protocol. Look at this. After all the complex setup, after encoding the witness into a giant oracle and reducing the exponential sums down, the human verifier only needs to make 2 queries to the model's circuits to prove its consistency. 2 queries, that's it. We have literally taken a doubly exponential problem, an interrogation that by all rights should take into the heat death of the universe to finish, and mathematically reduce the whole shebang down to 2 single questions. And here is the final, vital piece of the trap. When it finally comes time to evaluate those 2 queries, the verifier computes the direct evaluation. You'll see it right there. They do not ask the untrusted AI for the final answer. By directly evaluating these final points themselves and bypassing the untrusted AI completely, it becomes impossible for the suspect to tamper with the final test results. The trap snapshot and the math doesn't lie.
Section 6, towards safe scientist AI and the future of trust. So, we've successfully navigated all the abstract math. Let's bring this all back down to reality for a minute. Why did these researchers go through all this trouble to invent this interactive PCP protocol? Well, it's because of what we are trying to build next: safe scientist AIs.
In the very near future, we're envisioning these autonomous scientist AIs that will generate highly complex scientific hypotheses, assign probabilities to them based on real evidence, and then dynamically update those beliefs. But here's the thing. We cannot let these systems operate if they are secretly harboring contradictory logic, whether that's due to misalignment, bad training, or bias. This exact cryptographic framework we just explored is going to act as an internal guardrail. Before the AI is ever allowed to act or output a definitive scientific model, it will have to undergo this IPCP verification to prove its own internal consistency.
Which brings us to a really fundamental realization from the paper, and this is what I want you to really take away from all this today.
An incoherent model is not merely uncertain, it is internally broken. If an AI's beliefs cannot mathematically map to a single, coherent reality, it is inherently flawed. Deploying an inconsistent AI to make critical real-world decisions isn't just risky, it's fundamentally unsafe, because its underlying worldview literally just does not add up.
The authors actually sum up this existential danger absolutely perfectly with this quote: "Being highly intelligent and useful does not ensure consistency. We do not want highly intelligent systems whispering different things in our ears." And they hit the nail on the head. Just because a model gives you incredibly useful answers to your coding prompts or writes great essays does not mean it is structurally honest. We absolutely cannot allow superintelligent systems to manipulate us by offering conflicting realities depending entirely on how we happen to ask the question.
And that leaves us looking toward the horizon. The researchers have mathematically proven that it is possible to verify a model's consistency. But the next massive frontier in AI safety is this. Can we actually train AI systems to automatically generate these complex mathematical proofs of their own self-consistency in real time, as they reason? Just imagine a future where an AI doesn't just give you an answer, but simultaneously mathematically proves to you that it isn't lying to itself. Now that is a future worth building. Thanks so much for joining me on this explainer, and I'll catch you on the next one.